Hi everybody, today we're going to split up the lesson into two parts. We have a 2.4, 2.5 transformations lesson. Part 1, we're going to take a look at some basic functions, how we can manipulate them, and then part 2, we're going to focus a little bit more on inverse. In order to get started, we want to take a look at some of the basic functions that you should know from the past. Some of them might be a little bit new as well, depending on what your background is. But we know PreCalc 11 is full of graphing quadratics. So I'm going to go through these pretty quickly right here, but we'll get a chance to be able to fill in what our quadratic looks like. So as we start to transform functions, we want to be able to know what our basic function is, and then from there we can shift it and we can expand it, we can compress it, we can reflect it. There's lots of different things that we're going to start to do the next couple lessons. So for our basic quadratic, you can refer to your table of values, or if you've graphed a bunch of parabolas like you have in the past, you might be able to remember the slogan that we used to say: the amount you go over, you square to go up. So we fill in the table of values here on the side just for good measure. And we have our basic parabola right there. So we need that in order to be able to do parts of the lesson coming up. Just a review on parabolas in terms of the domain. You can put in any number for x and it'll produce something in which y is greater than or equal to 0. Taking a look at our square root function right here. Now, we haven't graphed too many square root functions in the past, but we know that the radicand right here cannot have a negative value for it to be a real number. So we're going to say that doesn't need to be there. Our x values, we picked perfect squares, and we picked perfect squares on purpose because when you square root them, they equal nice clean numbers. So if we plot this right here, we come up with something that's going to look like maybe half of a sideways parabola, and that's because it's the positive part of the square root of x. If it said plus or minus the square root of x, then you would see this additional part. Don't fill this into your notes, but you'd see this part come in here right there. So that is equaling y equals the square root of x, whereas this would equal y equals a negative the square root of x. In terms of what we want to be able to say just for this basic function, our domain is everything greater than or equal to 0, and our range is everything greater than or equal to 0. And if you want a quick way to be able to plot future points, you can always say the amount you go over, you square to go up. So if you pick a value like 49 for x and you square root that, you would go up 7 units. Okay, we have two more functions to look at right here. So an absolute value function, these bars right here, you may or may not be familiar with them. This means the absolute value. So if we say something like the absolute value of 5, you would say that is equal to 5. So by definition, absolute value is the distance to 0 on a number line. So if you have a negative value, like the absolute value of -3, we'll say that still equals +3. If you have something like the absolute value of 0, that's going to give us 0, though sometimes it just looks like we're saying lol. All right, not my best, not my best. All right, so what can we do with this right here? If we want to put in some values, we know that whatever you input for x right here, it's going to produce a positive value, or 0 in the case of inputting 0. But we put in 1, we get 1, 2, 3. If we put in -1 right here, absolute value of -1 is going to give us 1. Absolute value of -2 is going to give us 2. Absolute value of -3 is going to give us 3. So we start to plot these points, and you'll see that it makes the shape like the letter V. Okay, so we can extend that right here. Some of you may be saying, well, does that just look like graphing the line y equals x? except any of the values that are below the x-axis get reflected above, and that's true. Our domain is going to be all real numbers, and our range is everything greater than or equal to 0. So whatever you input for x stays the same, but whatever happens is your y value becomes the absolute value of it. All right. Finally, we have a reciprocal function. Okay, so reciprocal functions right here, the reciprocal of y equals x is y equals 1 over x. You'll remember some of this from our rational functions unit. If we put in 0 right here, we can't have 0 in the denominator. That is non-permissible. So we're going to say right here, there is nothing right there. And then if I put in 1, I get 1. If I put in a 2 right here, I get a half, and I get a quarter. Here I get -1, -a half, and -a quarter. And because we've done this before, I'm going to go through this a little bit faster. We have an asymptote at the line y equals 0, sorry, x equals 0, and we have that because we know x is not defined. As we plot our other points, we have the point 1, 1, the point -1, -1. These two are called invariant points. And if we plot further points from there, we would end up with something, and it starts to look a little bit like this. Now, because we've done this before, we can go a little bit faster. We actually have a horizontal asymptote drawn in right here. And that's because no matter what, you could not put in a value for x that is going to give you 0 for y. And that's just impossible. If you pick 1,000,000 for x or -1,000,000, it will still never ever be 0. Okay, so based off of that, we can say that our domain can be anything except 0, and our range can be anything except 0. Okay, we'll look at this final point here that says what happens with this point in a later example, but basically the point xy in each of these cases becomes the point x 1 over y. So why do we do all of this? We do all of this so we can start to look at transformations. So if you think about 2.1 to 2.3, we focused a lot on the algebra of transformations, working on function notation, composite functions. Now we're going to start to look at things graphically. And when we do that, we would say that there are 3 different types of transformations that we're going to focus on right here. So we have translations, expansions and compressions, and reflections. All of this we've done in the past, but we just haven't used this sort of terminology. So if you think back to what we've learned about with parabolas, when we took our basic quadratic function and we had it in the form of y equals a x minus h squared plus k, you'll remember a few of the things that we had. The point hk, that was represented by our vertex, and the point h in particular, this shifted everything left and right. So this would be where we found the x value of the vertex. So we're going to say this is going to be our translation left or right. And then the k value, that represented the y value of the vertex, so that's going to be our translation up or down. Now the a value serves several purposes. The first thing is we wanted to know if a was positive or negative. You'll remember when we had a positive parabola, we opened up, and when we had a negative parabola, we opened down. We would frown. So what we could say right here is a is going to tell us what we would call back then the direction of opening. Does it open up or down? But it told us a couple other things. So depending on the terminology that you've used in the past, if a was a value like 2 or 3 or 4, you'll remember that your parabola got stretched a bunch. And so a parabola that used to look like this all of a sudden got pulled up if you had a value that was a 2 or a 3 or a 4. And so what that means right here is A represented something called, well, some people will say it's a vertical stretch. For our sake right here, we're going to be consistent with Michelson. We're going to say this is a vertical expansion or a vertical compression. Okay, so what do we remember? If we have an example like y equals x squared and we transform it into y equals negative 2, x plus 4 squared plus 5, we can now say this. We have a translation 4 left and 5 up. We're going to open down and we're going to have what we would call a vertical expansion by a factor of 2. So what that meant is whatever your original y values were, you would double each of those y values to find out your transformed function from that. So we can expand this and we can take a look at shapes beyond parabolas. So if you think back to those basic functions that we had, and one of them was y equals the square root of x, what would happen when it becomes y equals 1/2 root x minus 1 minus 3? This 1/2 is consistent with the a value that we had in our previous question. And so we're going to say this means, well, if 2 meant that we had a vertical expansion by a factor of 2, then 1/2, this is going to mean that we have a vertical, not an expansion, but a vertical compression by a factor of 1/2. And then here, these were our translations or our shifts. So we're going to say right here, this is going to be a translation 1 unit to the right and 3 units down. Okay. Hopefully some of that's familiar from last year. We're going to do some justifications of that later in this lesson. So after you've graphed some of these functions that we've looked at, we could generalize this into a y equals f of x function. So we don't even know what this function would look like on a graph, but we know that y equals f of x has been transformed to become y equals negative 2 f of x plus 4 plus 5. And that should look familiar because those values are identical to the values that we had up here. The only difference is now instead of taking a parabola and shifting it, we're taking a random function, but we're doing those exact same shifts. So if you have y equals negative 2 f of x plus 4 plus 5, everything is going to stay the same from that previous example. So we're going to say we have a vertical expansion by a factor of 2. We're going to open down. Now, opening down is specific to a parabola. So this just means that when we open down for a parabola, you were reflecting it over the x-axis. So instead of saying opening down, we're just going to now say that we are going to reflect over the x-axis. And then finally, our translations are exactly the same. So we're going to say we will have a translation 4 left and 5 up. We can generalize this now looking at the parameters a, b, c, and d, and we can give some good transformations pre-calc 12 terminology to this. Okay, so let's start with the two most straightforward ones, C and D. So C was connected to the X, and it was how much that we would translate. So translation left or right. D is going to represent our translation up or down. A was representing, well, it would tell us if we reflect over the x-axis, and then it would also tell us if we had any sort of vertical expansion or compression. Now what's new is this B value right here, and we're going to explore that more. So I'm going to give you some of the terminology right here before we've actually explained what it can do, but we'll find out a little bit later what B value actually does. But I bet you could predict it. If A is representing the vertical expansions and compressions, then we're going to say here that B is going to represent the horizontal expansions and compressions, and instead of reflecting over the x-axis, it could tell us if we have a reflection over the y-axis. Okay, so again, this is just to label what everything is doing, and we're going to take a look at a few examples and we'll see what we can do to be able to explain this a little bit better. Okay, so now we have some true pre-calc 12 questions. It's going to tell us what's happening if you have the graph y equals f of x and it becomes y equals f of x plus 9. How do they differ from each other? I used to have y equals f of x. I now have y equals f of x plus 9. So we know back from pre-calc 11, this means that we've shifted left or right, and in this case we have gone 9 units to the left. Here we're going 7 up. Here we're going 4 to the right and 3 up. We want to isolate for y, so let's add 6 onto this side. So we're going 6 up. And we know that that is the same as having the plus 3 over here. So this would be saying we're going 5 right and 3 up. Okay, let's look at an additional example. Given the graph y equals f of x passes through the point 4, 7, what would happen when it's transformed to become 6, 6? Create a function that would represent this new function. Let's do a mini graph right here. So if we have the point 4, the point 4, 7 right here, 4, 7, and it's going to become 6, 6 somewhere right here. In order to go from 4, 7 to 6, 6, the easiest way to be able to see that would be to say maybe we went 2 to the right and 1 down. So if we went 2 right and 1 down, well, then this would be saying f of x has become y equals f of x minus 2 minus 1. 2 to the right and 1 down. Okay, let's try these. Write the equation of the image of y equals x to the 4 after a horizontal translation of 2 units to the left. Okay. Now I know this question sometimes trips up a few of us the first time we do this. If we go 2 units to the left, we could say it will become y equals, if this was an x squared and you went 2 to the left, you would write x plus 2 squared. And the only difference is now, instead of being squared, it's to the power of 4. So we could say y equals x plus 2 to the power of 4. There's 2 units to the left. For part B, we could treat these absolute value bars as we would treat brackets. We want to go 3 down and 1 to the left. So we could say y equals 2 x plus 1 minus 3. And then here we want to go 3 units to the right and then 2 units up. Okay, 3 units to the right and then 2 units up. Okay, so check those over with what you had, and hopefully we came up with the same solutions. So what we could start to do, and you'll see a lot of this in 2.4, 2.5, and 2.6, is we can now look at graphs. And we can now shift an entire function over. So if we had something like, well, f of x is becoming f of x plus 2 minus 3, well, all this means is we need to take our function and we need to go 2 left and 3 down. Let's highlight some of our key points. Now, a key point would be something like a maximum point, a minimum point. How about right here where we have some x-intercepts? And we take a look at that and let's move them 2 left, 3 down. And if you draw and connect these values right here, it's almost like using the copy or the cut and paste function that you would have, where you've now taken your original and you've just making your shift, and then right there we have our new function. Okay, we're going to go through these fairly quickly, but I just want to explain and justify a little bit of why these points do exactly what they do. So this next part is a little bit of theory right here. So if you have y equals x squared, so we're used to this, and you pick a point. So let's say we had the point 0, 0. Well, if you had y equals x squared plus 3, so you have this back value right here, and you retained values of 0 for x. When you put in 0 for x, you still get a y value of 3, meaning this is saying that we've gone 3 up. Whereas if you put in 0 for x right here, you get 0, negative 3, meaning you've gone 3 down. And that explains our vertical translations. Inside the brackets, a lot of times you'll hear a teacher or tutor say, well, just do the opposite. If it says x minus 3, that means you go 3 right. If it says x plus 3, that means you go 3 left. So we could think of it that way, and if that helps, that's great. But let's pick the point 0, 0 again, and then here's what we'll say. If I want to produce a value of 0 for y, what do I need to put in for x? What do I need to substitute for x to be able to keep my y value of 0? So right here, we know that if I substitute in 3 minus 3, I would get 0. So when I put in a 3 for x, I produce a y value of 0. And here, if I put in a negative 3, I produce a y value of 0. So in other words, if I used to have the point 0, 0, and I've now shifted over to 3, 0, I've gone 3 units to the right. And if I go to negative 3, 0, I know that I've gone 3 units to the left. Now, in terms of looking at expansions and compressions, there's vertical expansions, vertical compressions, horizontal expansions, horizontal compressions. When we define an expansion as being something in which it's getting bigger, so any value that would be greater than 1 is going to be considered an expansion, and a compression would be a number between 0 and 1. So something less than 1, we're going to say, let's keep it positive just so we don't confuse getting reflections involved in this operation here. But if you had something where you had a vertical expansion by a factor of 2, that means you're going to take your regular function and you're going to double that function. So you're going to put a 2 in front, which means whatever your answer is, you have to times by 2. So we put a 2 in front. If we want to half our answers, then we put a 1/2 right here. Now these next two are tricky and we haven't learned these, and we're going to explore them on the next page right here. If you were to predict, I would say 8 times out of 10 when you do this for the first time, people will not get this correct. A horizontal expansion by a factor of 2 is going to be expressed like this, the reciprocal of probably what you thought. So then this is going to be y equals f of 2x. Okay, so y is this the reciprocal of what we thought? Why is it the opposite of what we probably thought it was going to be? So let's take a look at that on the next page here. Before we do example 5 right here, let's go and let's do this justification right here. Okay, so if you have y equals x squared, let's pick the point in this case. Let's pick the point 1, 1. Okay, if we have a 2 in front of our function, and we substitute in 1 for x, the same value right here, you would get 1 squared times 2 would give us 2. In other words, the point that was at 1, 1 has now become 1, 2. It's doubled its vertical height, meaning we have a vertical expansion by a factor of 2. Whereas right here, if you had a half in front and you sub in that 1, 1 squared is 1 times a half is 1 half. And we would have something where we would only be going up right there. We'd only be going up half a unit. Whoops. So we're going to say that that is going to be a vertical compression by a factor of 1 half. Now, I know you've been waiting for this part right here. What's going to happen with our expansions and compressions for horizontal values? So let's do that same thing. Let's pick the point 1, 1. And if we have something right here and we want to say this, we want to retain an answer, a y value solution of 1, what would we need to put in for x for that to be true? Well, this x right here, it needs to be times, or it needs to be, substituted by 1 half in order for this to equal 1. Okay, let me say that one more time. So if we want an answer, we want this y value right here to say 1. And if we want that to say 1, we're going to need to times this x value, or replace, this x value by 1 half. And then that's going to give me my solution of 1. So if I put a 1 half in here, then that means that the point 1, 1 that I had over here is now going to be a half 1. And instead of going over 1 unit to the right, I'm only going half the unit, which means that right here, this is going to represent a horizontal compression by a factor of 1 half. If I have a 1 half in there already, so it's directly next to the x, just like this is directly next to the x, and I want to keep a y value of 1, then I could substitute in a 2 for an x. And if I did that, I would get a y answer of 1. So that means then that I would have this point all the way over here, where now my horizontal values have doubled. So when I have a 1 half in front of the x, right in front of the x, I now have a horizontal expansion by a factor of 2. Okay, we'll finish off today just by looking right here at what happens on a graph with these expansions and compressions. So we know that if it's in front of the function right here, this is a vertical, some sort of vertical stretch. So this is our vertical expansion by a factor of 2. Whereas right here, that is not in front of the f of x. That is changing what's happening with our x value. And when it changes our x values, that is something that's a horizontal expansion or compression. And we just learned that that is going to be the opposite of what it looks like. So that's a horizontal compression by a factor of 1 half. So how would we adjust this right here? If we have a vertical expansion by a factor of 2, we're going to plot our key points right here. And now we want to double the y values. So vertical expansion by 2, you keep the same x values, and when you double your answers. So here's the 3, so that becomes 1, 2, 3, 4, 5, 6. Our negative 3 down here, 1, 2, 3, 4, 5, 6, becomes negative 6. And then these points on the x-axis, when you double 0, you just stay exactly there. And you create something that's going to look like it's been stretched twice as much as what it used to be. So for a horizontal compression of 1/2, let's highlight the same key points. And we're going to half the x values. So whatever your original x values are, you're now going to half. So if that has an x value of -1 right here, that's now going to be -1/2. That's going to be +1/2. This guy at 0,3 is going to stay the same. And 3,0 is going to become 1.5 0. So we get something that looks like that. Okay, we're going to stop right there. That's part 1 of 2.4, 2.5 transformations. I hope you enjoyed the lesson, and I'll see you guys later.